Now that you are familiar with the basic vocabulary of networks, hosts, links, and packets, it is time to go deeper into two fundamental concepts that underpin virtually every communication on the Internet and on private networks: the Internet Protocol address and the structure of a network packet. Understanding these concepts is not just theoretical knowledge. As a future cybersecurity and DevSecOps specialist, you will rely on them every single day to analyze traffic, detect intrusions, conduct penetration tests, and configure secure infrastructures. What is an Internet Protocol address? An Internet Protocol address, commonly called an IP address, is a numerical label assigned to every device connected to a network that uses the Internet Protocol for communication. Its purpose is twofold: identifying the host or network interface, and providing the location of that host in the network, which makes routing possible. Think of it like a postal address. When you send a letter, you write the recipient's address so the postal system knows where to deliver it. An IP address works exactly the same way for data traveling across networks. There are currently two versions of Internet Protocol addresses in use: version 4, written IPv4, and version 6, written IPv6. Both serve the same fundamental purpose but differ significantly in format, capacity, and some technical features. Internet Protocol version 4, IPv4. IPv4 is the older and historically most widely used version. An IPv4 address is a 32-bit number, which means it is stored as 32 binary digits, zeros and ones. For readability, it is written in a format called dotted decimal notation, where the 32 bits are split into 4 groups of 8 bits, each group converted to a decimal number between 0 and 255, and separated by dots. For example, the IPv4 address 192.168.1.10 is made up of 4 numbers: 192, 168, 1, and 10. Each of these numbers represents 8 bits. The total number of possible unique IPv4 addresses is approximately 4.3 billion, precisely 2 to the power of 32. At the time IPv4 was designed, this seemed more than sufficient, but the explosive growth of the Internet has led to a critical shortage of available IPv4 addresses. IPv4 addresses are divided into two parts: the network part and the host part. The network part identifies which network the device belongs to, and the host part identifies the specific device within that network. To determine where the network part ends and the host part begins, a subnet mask is used. A subnet mask looks similar to an IP address. For example, the subnet mask 255.255.255.0 means that the first 3 groups of numbers, the first 24 bits, represent the network, and the last group, the last 8 bits, represents the host. A device with IP address 192.168.1.10 and subnet mask 255.255.255.0 belongs to the network 192.168.1.0 and has the host identifier 10. Subnet masks are often written in a shorthand called classless interdomain routing notation, or CIDR notation. Instead of writing the full subnet mask, you simply write a slash followed by the number of bits used for the network part. For example, 192.168.1.10 out of 24 means the same thing as 192.168.1.10 with subnet mask 255.255.255.0, because 24 bits are used for the network. Some IPv4 address ranges are reserved for special purposes and will never be routed on the public Internet. These are called private address ranges. The 3 main private ranges are 10.0.0.0 to 10.255.255.255, also written 10.0.0.0 out of 8, 172.16.0.0 to 172.31.255.255, also written 172.16.0.0 out of 12, 192.168.0.0 to 192.168.255.255, also written 192.168.0.0 out of 16. When you mapped your home network in the previous activity, the addresses you found were almost certainly in the 192.168.x.x range. These are private addresses used inside your home or office network, invisible from the outside Internet. Another important reserved address is 127.0.0.1, known as the loopback address. Any traffic sent to this address is looped back to the same device and never leaves it. It is used to test network software locally. If you type 127.0.0.1 in a browser on your computer, you are connecting to a web server running on your own machine. The broadcast address is another special address. In a network using the subnet 192.168.1.0 out of 24, The broadcast address is 192.168.1.255. A packet sent to this address is delivered to every device on that subnet simultaneously. Internet Protocol version 6, IPv6. IPv6 was designed to solve the address exhaustion problem of IPv4. An IPv6 address is 128 bits long, which provides approximately 340 undecillion unique addresses, a number so large it is considered practically inexhaustible. IPv6 addresses are written as 8 groups of 4 hexadecimal digits, separated by colons. For example, 2001, 0DB8, 85A3, 0000, 0000, 8A2E03, 7073334. Hexadecimal notation uses the digits 0 through 9 and the letters A through F to represent values from 0 to 15. IPv6 allows several shorthand rules. Leading zeros in each group can be omitted, and one or more consecutive groups of all zeros can be replaced by a double colon. So the address above can be shortened to 2001:DB8:85A3:8A2E:370 to 7334. IPv6 also has its own loopback address, 1, which is equivalent to 127.0.0.1 in IPv4. While IPv6 adoption is growing steadily, both versions coexist today, and many networks use both simultaneously in what is called a dual-stack configuration. What is a network packet? A network packet is the fundamental unit of data transmitted across a network. Instead of sending data as one continuous stream, networks break data into small, manageable chunks called packets. This approach, called packet switching, is more efficient and resilient. If one packet is lost or delayed, only that packet needs to be retransmitted, not the entire data stream. Every packet is structured into distinct sections. The two most important are the header and the payload. The header is the control section of the packet. It contains metadata, information about the packet itself, that allows network devices to handle it correctly. The payload is the actual data being transported, such as a portion of a web page, an email fragment, or part of a file. At the Internet Protocol level, the packet header contains several critical fields. The source IP address, the IP address of the device that sent the packet. The destination IP address, the IP address of the device that should receive the packet. The time to live field, in IPv4, a counter that limits how many network devices, called routers, a packet can pass through before being discarded. Each router decrements this counter by 1. If it reaches 0, the packet is dropped and an error message is sent back to the sender. This prevents packets from circulating indefinitely on the network. In IPv6, this field is called hop limit. The protocol field indicates which higher-level protocol is carried inside the payload, for example Transmission Control Protocol, TCP, or User Datagram Protocol, UDP, the total length of the packet. A checksum, in IPv4, to verify the integrity of the header. Here is a concrete example. Imagine you are browsing a website. Your browser sends a request to the web server. That request is broken into one or more packets. Each packet has a header containing your computer's IP address as the source, the web server's IP address as the destination, a time-to-live value, commonly set to 64 or 128, and the protocol identifier for TCP. The payload contains the actual request data, such as the HTTP message asking for a web page. The web server receives the packets, reassembles them in the correct order, using sequence numbers from the TCP layer above IP, processes the request, and sends back a response in the same packet-based manner. Why packet structure matters in cybersecurity. Understanding packet structure is absolutely critical for cybersecurity professionals. When you use tools like Wireshark, a network traffic analyzer, you are reading the raw content of packets traveling across a network interface. You can see source and destination IP addresses, protocol types, time-to-live values, and payload contents. Many attacks manipulate packet headers directly. For example, in IP spoofing, an attacker forges the source IP address in a packet header to make it appear the packet is coming from a trusted or different source. This is used in denial-of-service attacks and to bypass filters. In a time-to-live-based attack, an attacker can craft packets with specific time-to-live values to map out the topology of a network, discovering how many routers exist between the attacker and a target. Packet fragmentation attacks exploit the way large packets are split into smaller fragments. An attacker can craft overlapping or malformed fragments to confuse firewalls or intrusion detection systems. When conducting a penetration test, Your first step is often reconnaissance, which involves analyzing packets and IP addresses to understand the target network structure before attempting any exploitation. Routing: how packets find their way. When a packet leaves your computer, it does not travel in a straight line to its destination. It passes through a series of network devices called routers. Each router examines the destination IP address in the packet header and decides which direction to forward the packet, based on a routing table, essentially a map of the network stored in the router's memory. This process is called routing, and it is what allows packets to travel across the entire Internet, hopping from router to router until they reach the correct destination network, and finally the correct device. For example, a packet sent from a computer in Paris to a server in New York might pass through a dozen or more routers, each one forwarding it a step closer to its destination based on the destination IP address. Key concepts to remember. To summarize the essential points of this lesson, an IP address is a unique numerical identifier assigned to every device on a network, used to identify the device and enable routing. IPv4 addresses are 32 bits long, written in dotted decimal format, for example 192.168.1.10, and support approximately 4.3 billion unique addresses. IPv6 addresses are 128 bits long, written in hexadecimal groups separated by colons, and provide a virtually unlimited number of unique addresses. Private IPv4 address ranges, 10 XXX, 172.16, XX to 172.31, XX, and 192.168.x.x, are used inside local networks and are not routable on the public Internet. The loopback address 127.0.0.1, IPv4, or 1, IPv6, refers to the device itself. A subnet mask or CIDR notation defines which part of an IP address identifies the network and which part identifies the host. A network packet consists of a header, containing metadata such as source and destination IP addresses, time to live, and protocol type, and a payload, the actual data. Packet switching breaks data into small chunks for more efficient and resilient transmission. Routers use the destination IP address in the packet header to forward packets toward their destination. Understanding IP addresses and packet structure is foundational for using tools like Wireshark, conducting penetration tests, detecting attacks such as IP spoofing and fragmentation attacks, and securing network infrastructure.